Hi, good morning, everyone. I'm absolutely delighted to be here. It's my first visit to ICTS, and to a complete fortunate alignment of circumstances, this happened, and it's a very, very exciting time in our understanding of black holes. Of course, my interests have been on the supermassive cousins of the lighter black holes. And I wanted to say hi to many friends in the audience. Hi, Prajwal. Hi, Suchetna. I wanted to say thanks to Bala and Ajit for helping with all the logistics and the endless emails, getting things done. So without much further ado, what I decided might be sort of an interesting approach to bring everyone up to speed on how we've been thinking about the formation. So there are three big questions, sort of the meta questions, which are how do the first black holes that are the progenitors of the supermassive black holes that we are now ubiquitously detecting across cosmic time in the universe, how they actually formed and how they grew. And the question of the growth is, all of these, there are many, we understand a lot, but there are many, many open questions in these three big meta questions. The second question is, of course, how they grow, and in particular, how the fuel actually reaches black holes. And you will see during the course of these lectures that there are many issues there that are not resolved. You would think that at this point, with the kind of data and the kind of tools that we have, that we would know a lot more and in a lot more detail than we currently do, which is actually a good thing for researchers wanting to enter the field. So it's not a field where everything is stitched up at the moment. And then finally, it turns out that black holes, as we'll see during the course of these lectures, I'll be showing you a lot of what I think are key pieces of data that inform the modeling. So my approach is quite phenomenological. So I use a lot of different data sets, multi-wavelength data sets, and try to extract the information that is relevant to doing a model for a population of growing black holes. So the idea here is to try and understand the reason we want to look at a population, even though we have exquisite data for individual accreting sources, is the fact that we now know that almost every galaxy in the universe harbors a central supermassive black hole, and that there are these correlations that are seen with the properties of the galactic nucleus in which a supermassive black hole is growing that suggest a deeper connection, deeper physical connection between the assembly of the black hole and the formation of stars in galaxies. And we have a very good framework, as you all know, for the understanding the overall structure, formation, and assembly in the universe. So integrating supermassive black holes into this framework means that we have to understand both the impact of the environment, the larger scale environment on the assembly of these black holes, as well as the feedback, the energetics, the relevant energetics from the accreting black hole that exerts and couples energy on a lot of different scales potentially, because we see phenomena on different scales that suggest that there has to be a coupling. So these are sort of the big questions, and we've been going at these big questions, as I mentioned, using data in two different ways. So using deep understanding, multi-wavelength understanding of individual accreting sources, so individual supermassive black holes, both dormant and accreting black holes, just measuring the masses, measuring the properties, and then trying to model the population in the larger context of hierarchical structure formation in a cold dark matter dominated universe, given the all other features of our universe that are very well pinned down. Of course, no matter that there are some questions like what is the nature of dark matter, we have this entire model that's predicated on the growth and assembly of dark matter halos that host the galaxies, that host the black holes, and we don't know what the dark matter is, but we will not worry about that niggling thing at the moment. And we'll focus really on black holes. So the way I've structured the three lectures, so today I just wanted to start off with complete basics. So I know there are people with different levels here. There are obviously experts in the audience, but I pitched them at the level of a graduate student who is looking perhaps, has dabbled a little bit and is possibly looking to start working on problems. So that's sort of the level at which I pitched. And so feel free to interrupt at any point if something's not clear. Happy to help. So this is sort of the outline that I have. So as I said, I want to look at some sort of basic properties of black holes and basics of our understanding at the moment. And I have to say I have quite a few slides on primordial black holes, but I will skip through them fairly quickly, and I'll tell you why. Because this entire approach that I've outlined to you, where you look at phenomenology, you look at data, then you constrain the model, there are absolutely no constraints at the moment, no credible constraints on supermassive, on primordial black holes as seeds for the supermassive black holes. It's unclear whether there are no constraints at the moment that are testable, observationally constrainable for the mass function of primordial black holes that could form early on in the universe. Therefore, but there are some interesting theoretical ideas, so I will show you some of those ideas. And then there is a niggling problem of intermediate mass black holes. So this is a population of black holes with masses in the range of 10 to the 4 to 10 to the 6 solar masses, which we believe should be much more ubiquitous in the universe than they really are. And so the question is, are they just hidden, or do black holes actually grow too rapidly that you don't see a lot of them sitting around in that mass range? So that's, so we'll come to some of those questions. And then, of course, supermassive black holes. Then I'll talk a little bit about our current paradigm, like our current understanding of how black holes grow and the Eddington limit, and talk a little bit about the feeding disk, the accretion disk, the kinds of models that we have, and then some new phenomena that we have started studying much more theoretically, which is super Eddington flows and rapid growth of early black holes and intermediate redshift black holes. And so, as I said, almost everything is constrained by data that we have and that we know, but there are going to be a few topics here and there where the theorists are a little bit ahead of the game. So for example, we are yet to detect a supermassive super Eddington source in the universe. But it offers a very interesting proposition in terms of rapid mass assembly. So I've listed a couple of reviews. So many of I even have many slides that I have borrowed from these very excellent sources, and I know that this book, it has come out, their lectures from SASFA have actually come out as a monograph, so, and it's available. So I urge you, and as we go along, I'd be happy to suggest, if people want to delve deeper into some aspects, what useful reviews are out there. And so this is what I plan to do in the first lecture is this. In the second lecture, I will delve much more deeply into trying to model the connection between the very small scale physics right around the black hole to the larger scale physics, sort of galaxy formation processes, with a view to trying to make sense of observationally detected correlations between properties on the small scale and the large scale. And in the final lecture, I'm going to focus much more on, it's going to be more of a personal take on sort of my views and sort of a lot of the work that me and my research group have been doing for the last 10 years on the formation. So I'll talk to you, I give you a lot more in terms of, lay out what the open questions there are, formation of the first black holes, and what might be interesting avenues. Yeah, actually there was a question there, yeah. There are many candidates. No, they're there. They're very much there. There are many candidates, and there are 2 detections that I think are very credible. And I think these 2 detections are suggestive that we've been looking in the wrong place. So we've been fixated on looking in the centers of galaxies. The 2 candidates that have been found that are really credible candidates have been in the outskirts of galaxies. So these intermediate mass black holes, as I mentioned, as I alluded to earlier, might be a fairly short-lived stage. And so these might be best detected sort of slowly swirling in the halos of galaxies and making their way into the central. So it may be an issue of we've been looking at the wrong place. I mean, it's the case of the drunk under the lamppost, right? We've been looking at the place that's been most convenient and easy to look at. And so I think that there ought to be a population of intermediate mass black holes. And when the third lecture, when I talk about formation mechanisms, we might have some understanding of why they've been so elusive. Because it turns out that black holes in the mass range 10 to the 4, 10 to the 6 solar masses, if they are embedded in extremely gas-rich environments, can grow very rapidly. So you wouldn't see them at that mass. You'd see very few of them centrally in that mass. You could see a lot of them loitering in halos. So that is much harder, of course, observationally to detect. And so, occasionally, like in the case, I'll show you that particular case where I think it's a very nice observation of two merging galaxies that have merged recently. And you see one sort of in the outskirts. So it's spilled out of one galaxy, and it's now starting to make its way into the merger remnant. So give me a question. Yes, because I focused on supermassive black holes because I thought, yes, I deliberately, right? So I hope that's okay. And because, there are many of you. Yes, yeah. And I think that I will talk about that in the third lecture, that, for your garden variety central supermassive black holes like the Milky Way, 10 to the 6, 10 to the 7 solar masses, you could start out with stellar mass black holes and grow them over cosmic time. It requires special sets of conditions to line up, but those are available in the early universe, and you could do that. But by and large, for the most massive end of the black hole population, supermassive black hole population at every epoch, you actually require some additional set of circumstances. Most likely, and that is my belief, and that is a set of predictions we have out there that should be testable with even the James Webb Space Telescope, is that there needs to be a channel for making initial massive seeds for black holes. And I think the evidence has been growing in that regard. We proposed with one of my former postdocs, Giuseppe Lodato, we proposed sort of an early model to make these they're called direct collapse black hole seeds. It was considered highly speculative at that point because, it was, the computation was not up to showing how you could actually make them. So it was sort of a slightly hand-wavy theoretical model. But over time, both the data is pointing in support of more than one way to make black holes. And I thought one of the interesting things, look, there's a lot of exciting activity in India already in LIGO, but I think what would be lovely to gear up for is LISA. And so my sort of focus has been, and I'm on the NASA LISA science team in the US, and our goal has been to try to get a lot of younger people to start thinking about supermassive black holes. And, and I should tell you that I obviously have a fondness for supermassive black holes because not that there's a contest between the lower mass cousins and the overweight supermassives, but I think what is exciting about the supermassive black hole candidates is their mergers will have a very rich multi-messenger signature. Not only will we see the gravitational waves that LISA will detect, much lower frequency than LIGO, which is why we need a space mission, but also that they will inevitably almost always be electromagnetic counterparts. So they will not be dark mergers in the sense that because galactic nuclei are so gas-rich, you expect to see both a precursor to the gravitational wave signal and a postcursor. So you can nail down where the merger occurred and properties of these supermassive black holes with much greater efficiency in this particular case, only because you have those associations. And I think, I don't know if you all saw, recently ESA has decided to actually line up Athena and LISA. So Athena is an X-ray mission, which should detect active accreting black holes, and LISA, so that they will be flying at the same time. So we should be able to get a very rich data set, multi-messenger data set for supermassive black holes. And of course, what's happening with LIGO is spectacular, right? There's this beautiful event last night. I don't know if you guys saw it on GraceDB. So it looks like a very nice black hole neutron star event.
Just a final clarification. So you're the primordial black holes, you're thinking about a heavier one.
No, they're very light. So as I told you, everything about primordial black holes is speculation. And so these would be, primordial black holes are only invoked as they would grow. So they wouldn't remain, we believe they have to start out with tiny masses to not have evaporated and to be hanging around. So I'm going to talk about them very much in the context as providing seeds, initial seeds for the supermassives that we see at late times. I think, I'm not going to touch upon, I might have something on it, but I'm not going to touch upon this idea, interesting as it was, but which is, not as important, which is having all of dark matter be primordial black holes, i.e. surviving population of primordial black holes to today. I'm not really going to be talking about that, yeah.
You can still have lighter because you have a longer time.
Yeah, no, the problem is that what you could have is that there's a sort of contrived model that Simeon Bird, Mark Komiankowski, and others proposed, where they suggested that you could just arrest the growths of these primordial black holes, and you could grow them from like 10 to the 15 grams or so, which is where you start out at inflation. You make them at inflation, and then somehow you arrest their growth through cosmic time, through all the epoch of ionization, everything, and then eventually you grow them to about 100 solar masses, between 30 to 100 solar masses, and this was motivated by the LIGO events. That the usual stellar mass channels, binaries, et cetera, were not producing, do not actually produce as massive black holes as the first set of LIGO events was showing us. And so they came up, they said, maybe that there is a completely different channel to make them more massive, sort of 30 to 100 solar mass. And it turns out there is a small window of, between 100 solar masses to about 1,000 solar masses where you could hide, as a population, you could hide a lot of not a lot of black holes in terms of omega matter, but a lot of black holes in terms of being able to explain maybe a fraction of the dark matter and maybe the LIGO event. So that work was motivated very specifically.
I'm just wondering, when you said arresting the growth of these, is it possible, is that the mechanism that maybe you can balance the evaporation with some kind of...
No, it was very contrived. Yeah, so these would be the population that would not actually evaporate. These would be the guys that would actually survive. The problem with the primordial black holes has been that how do you prevent them from growing in the gas-rich early universe? So you have to do something to prevent them.
So that's why I was wondering whether you...
The timescales don't work out for evaporation, and the timescales are really out of sync, yeah? That's right. There'll be, there's no, it would have to be way too finely tuned, black hole by black hole, not even for the entire population, because it's so environment dependent. Yeah.
Is that a reason not considering extremely sub-Eddington accretion?
Yeah, I will talk about that. I will talk about that. So I will talk about that in the final, when I talk about the final, in the final lecture, I will talk about, slim disks. And so I'll talk about obscured accretion. Yeah, slim disk. Oh, extremely sub-Eddington flows, sure. So I think, So what I will show you is the formalism, and the formalism works. The geometry will be different, but the formalism works even if the flows are very sub-Eddington. So the thing that really changes, pardon?
Like Sagittarius,
Yeah, Sagittarius, and so on and so forth. Yeah, so I think what I'm going to lay out are sort of the basics, right? So, as I said, you should pardon me if a lot of the, if it's going to be, much of it is going to be repetition and known stuff for many of you. It's trying to get everybody on the same page. Okay, so the key challenge, you might say, okay, what is the real challenge? And the challenge for supermassive black holes has been the integration of scales on which we need to model the physics and to get a full synthetic picture. So if you take the supermassive black hole at the center of the Milky Way, 4 million solar masses or so, then you find that the Schwarzschild radius is about 10 to the 12 centimeters, and then you cascade out in scales and you look at the larger scale environment, you find that there's almost 14 orders of magnitude out to which you need to understand the gas flows in order to really figure out what is the feeding of the central supermassive black hole. And you can see, because of this range of scales, we still don't actually know, given an m dot, a gas accretion rate at any one of these larger scales, what is the actual flow at, say, 1,000 times the horizon. We don't actually know that. There are no models that can actually link cosmic large-scale megaparsecs, so we see these gas filaments, we see all that phenomenology in the universe, both in the data and in simulations, but going from there all the way down to the feeding and therefore the final mass accretion history, there are big gaps, okay? And we make assumptions and we connect. And the way the approach has been so far has been to start studying phenomena at about 10 to the 5, 10 to the 6 Schwarzschild radius. And that is where we think we understand some of the physics incredibly well. And then on the very large scales, you have these large simulations, like the ones that Suchetna and others do, where we know those are sort of the initial conditions, if you will, for the next scale in. So we've been trying to cascade, put models, use the outputs of models as inputs for the next scale, and so on, and try to build as much as we can. And there are inherent limitations in what we can do at the moment, but with the growth in computation, wouldn't you say, Suchetna, in the last 5, 10 years, tremendous progress, right? Just tremendous progress, just in terms of CPU power as well as techniques that are available and observational constraints that allow you to partition the parameter space and say, look, don't need to worry about that. Let's look at, let's focus here. And so I think it's really been phenomenal what's happened in the last 10 years, both in data, and so things have really taken off. And in fact, what I think has been really interesting, so my PhD, which was now 2000, I finished my PhD in 2000, so 20 years ago, so was the first, I did the first models sort of integrating these scales, integrating black holes into the larger cosmic picture. Because the only thing that had been found at that time for a population of black holes was in 1998, they found a correlation between the mass of the central supermassive black hole, these are dormant black holes in the nearby universe, and the properties of the galactic bulge in which they were sitting. So there was this correlation, it was called Magorian et al. Published this correlation, that was the only thing that was known. And so what was clear is somehow black hole activity correlated to larger scales and was connected with galaxy assembly history, right? So, but from then to now, progress has been tremendous. So anyway, let me just quickly start off. Many of you probably know this, that the idea of there's another big disconnect that we in astrophysics have to kind of bridge, which is a lot of the models, except for the simulations that are modeling very, very close into the Schwarzschild radius. They are going down to 1,000 Schwarzschild, these GR-MHD simulations. Much of the astrophysics I am going to talk about is classical astrophysics, where GR is not really relevant. GR is relevant for the overall black hole problem, obviously, but there are scales that you can decouple, and we just do classical astrophysics, right? And so I think that those connections, this connection of what is going on with the curvature of space-time and how that might affect the coupling of the gas, the energetics of the gas that flows in, is not as well understood as we would like at the moment, right? But remarkably, what we do have are very good descriptions of what the black hole is in terms of what it does to the geometry, and the fact that we, from astrophysics, the insights that we've been able to provide for more fundamental physics has been mass measurements for black holes. We've been able to come up with masses for black holes, measured in a bunch of different ways, right? And so as you all know, the Schwarzschild solution, which is basically the solution for the space-time geometry around a point mass, was found, this solution, this exact solution to Einstein's field equations was found very soon after Einstein presented the general theory of relativity. And you have all seen this form, and this form is very suggestive in the metric when we write out the geometry right around this singular mass, m, as shown here. And you all know that the theory is incredibly well tested, and that this formalism actually holds quite well. From the point of view of classical astrophysics modeling for black hole, I think the radii, the inner region, And the properties of the inner region that are relevant to us are a bunch of scales, right? So the scales that are important, the first one is, of course, the horizon, the event horizon or the Schwarzschild radius. And then what is relevant is the photon radius, which is about 1.5 times the horizon or so. And this, as you all know, is a region where light orbits, you have eternal light orbits. And then you have regions beyond that where light just grazes past, and you might see gravitational lensing effects. But so these are sort of the essential scales for the inner region. And as I mentioned, it's good to keep this in mind because whatever astrophysical flows we're going to talk about at large radius are going to impact, we want to try to get as close as we can to here. And, and we have reasonable success. And so at the moment, so this is my nod to stellar mass black holes, yeah.
Imaging of black holes, all these things are extremely important.
Absolutely, of course. As I'll show in my final lecture when I sort of tie together, so for example, the reason it was not all just hype with the Event Horizon Telescope image. It was quite a remarkable image, not just for the technical feat of having produced it in the first place, but it was the first test that showed us this whole accretion story is actually works, because you can actually see gas in the proximity of the black hole. So gas does make it all the way close to the black hole, and so on. So our fundamental paradigm was sort of validated in a way that we had taken it for granted. So that was a very important and powerful image. And that was as close as we have gotten to any supermassive black hole. So, yeah. Yeah, up to there we can do classical. But even for the light deflections, it's GR. So for the deflections you still need GR. So these are the three scales on which general relativity is actually important. And anywhere outside we can make approximations and ignore GR by and large. Not for everything, as we'll see a little later, but by and large. And so the picture that I'm going to be focusing on is one where we have telescoped out. So this stuff is sitting in a black box in the center, and we are going to work on everything that is outside and try to get the gas down as close as we can to this. And then we don't know what to do, quite. So let me just quickly give you a flavor for where we are in terms of the inventory of black holes in the universe. So as you all know, we have a good census of stellar mass black holes, and we know of their existence from the LIGO data, of course, now, as well as we had clues from the X-ray data in many X-ray binaries. So we kind of have a mass function. This is like a toy. This is not. Don't ask me why there are no error bars or whatever. This is just to give you an idea that this is, as a theorist, one of the things you want to do. Any project I work on, I actually have a plot that I want. What is the plot that you desire, right? What do you want to extract in a problem? What is the basic that you want to understand? So obviously the dream plot for a theorist is to have an initial mass function for all black holes. So ideally what you want is, the plot that I would really like for us to have is for every galaxy that you can start out with, every individual galaxy, it would be really nice to have the inventory, the initial mass function of black holes in it. So presumably ton of stellar mass black holes, few intermediate, and then maybe the supermassive that is sitting here, maybe 10 to the 6 or something like that. So ideally you want, I have no idea what this should look like. Okay, this is just a guess. We just know there's a lot of stellar mass black holes. I mean, the universe appears to be littered with black holes, basically, and every galaxy is littered with black holes. And I recently just saw, and you might have seen the early release images of Rosetta. It's incredible. You just see black holes everywhere. So this is sort of the dream plot that we would like to be able to produce so that we can have a full mass inventory of black holes. Yeah. Oh, as in, I didn't mean the initial formation. It's a snapshot. So I want to look at the Milky Way, And I would like a census in the Milky Way. If 10 to the 12 solar masses is the mass of the dark matter halo, 10 to the 10-ish, whatever is the mass of stars, 10 to the 9-ish is the mass of gas, I would like to know, yeah, now. Because then, you know, you want to, all we have in the universe is snapshots. So then we have to build evolutionary histories that will then combine, right? And ideally, it would be useful and interesting if, obviously, supermassive black hole growth is tied to star formation. Star formation is what gives you the stellar mass black holes. So they have to all be related at some level, right? So we would like to ideally have a picture where we can put together all the ingredients. And you know, I would like a plot where for every galaxy, I would like an inventory of the omega, contribution to omega from each of the components in that individual galaxy. That would be awesome. I think we're moving in that direction, and I think probably in 2 decades, we could be pretty close to that. Maybe not for every galaxy in the universe, but for some, at least definitely local galaxies, we should have that census. So, and then we know, for example, that we have evidence, observational evidence from the Milky Way, from bright quasars, and in fact, now we know that there are extremely massive central black holes that could be up to a few billion to maybe, you know, 10 to the 10 solar masses. Yeah, no, those color codes are just there. I'll show you when the thing gets filled in, right? So it's supposed to sort of show you many different ways of making them and how the mean, median shift for, yeah. So that's, no, notice I have not put any units. This, pardon?
The number of SMBs are much smaller than the stellar mass black holes, right?
Right, absolutely, absolutely, yeah. Much more in number, yeah. But, you know, in terms of the mass density, the stellar masses outweigh, absolutely. It's just like the luminosity function in galaxies, right? So if you look at a cluster of galaxies, you have a lot of low luminosity galaxies and only a few of brighter ones. Okay, so these colors, as you can see, were just to show you possible. No constraint, so that is just the speculation. They could be important in terms, it could be as large as that. They're actually quite unconstrained at the moment. So you could have, and the reason this was made to look large is if this was in the context of the idea that all dark matter is made of primordial black holes, right? In which case, yeah, so that's the optimistic. Yeah, so this was just a sort of, you know, hand-wavy plot, but to show you sort of what the dream plot would be, right? No, not at all. We can talk more about that offline, yeah. You know, at most, where we are at most is that between 1 to 5% of the total dark matter of a galaxy could be comprised of primordial black holes. Yeah, but you know, 1 to 5%, it could be mismatched socks, right? I mean, 1 to 5% is just not interesting at all. But yeah. No, as I told you, this is a snapshot. So in terms, this is not an evolutionary plot, right? So it could be that you make a lot of them early on, but if you look at how many might survive as an inventory today, this is like for that dream plot, like what would the census be? Yeah. Sorry, what? No, it's not suggesting all of them are. The evidence, the observational evidence for that bump, for that mass range, pardon? Sure, yeah, QPOs and so on, yeah, sure. What are you, no, I'm missing something. Yeah. Yeah.
Yeah.
Yeah.
As we know, mass cannot be hiding in the time space.
Yeah.
It may not be ULS, I mean,
Yeah, but I'm not making any statement about ULXs or which systems harbor which kind of black holes. All I'm saying is that the observational evidence for this part of the diagram is coming from these kinds of sources, right? And the observational evidence for, as I told you, there's one very credible source for an intermediate, two of them actually, and they are from NGC 1313. And so, this is just to show you that there is some observational support for certain mass ranges. This is not suggesting these are the only ways, or that, you might immediately say, but not all supermassive black holes are quasars. Obviously, many are obscure, et cetera, et cetera. Yeah. It could be, but what is not clear is whether the cases where intermediate masses are suggested for bulgeless galaxies, whether these are just cases where you have seed black holes that have stagnated. So these are black holes that have just lagged and that haven't grown since their initial seeding early on. So it's not clear whether there's a very large population that is sort of sitting around at that mass range today. So I keep saying, right, that I think that there may be a lot of initial mass, intermediate mass black holes made in the very early universe, and possibly throughout cosmic time. So those are models, actually, when I talk about my work, I'll talk to you about what are the current ideas that we are pursuing. So one of the frontiers that we are pursuing, which is hard theoretically to get our heads around, is that there is no reason, all the models that I'm going to show you for most of the talks and the work that has been done so far assumes that you have like an epoch, early epoch, you form black holes, and the seeds keep forming, the stellar mass black hole seeds keep forming throughout cosmic time because that's the end states of stellar populations, right? But the supermassive seeds that form, we think form at an early time, and then that's it. You don't form any more massive beyond the stellar mass black holes. But now we think that there may be conditions permitted in galaxies where you might be making intermediate mass black holes, not centrally perhaps. So that's the thing. I think, so we are looking for ways in which you can make them at late times, and not in the center. You make them outside in situ, and then they're lingering and they're slowly making their way in. And maybe that's why we have not seen the majority of them. And the few cases where we see them are the ones in which they have made their way in and they have lodged themselves as the centrals. So those are sort of ideas at the moment. These are not, this is just work in progress. And I'll show you some nice results, early results. Yeah. There could be, and I'll show you why. Yeah. Yeah, well, I mean, again, this is none of this, guys. This is just a cartoon. Okay, don't take it very seriously. It is just to show you that, as a theorist, one of the key questions you want to answer is what is the inventory of black holes, right? So that dashed line that I put there is very suggestive that, it's not just the sum here, right? I have a higher amplitude. And it's suggestive because, as I was just responding, I think we have some new exciting ways to make more intermediate mass black holes over at later times in the cosmos. So I'm just kind of adding, bumping that up. Yeah. Yeah, where they are. Yeah. Yeah, most likely. Yeah. Yeah.
So, since you put in constraint on the primary lines, so there have been certain more accreted dark matter as primary. So you don't think they're...
None of the models are viable. No. Yeah. I personally don't think they're viable at all. They're extremely fine-tuned. I mean, it depends. If you don't care about fine-tuning, yeah, sure. As I said, if you don't care about fine-tuning, you could have 1% of the mass of the typical dark matter in a galaxy like the Milky Way locked up in primordial black holes. But then, you could have 1% in brown dwarfs. I mean, Macho told us that you could have 1% in brown dwarfs. So to me, that's not interesting. It would have been interesting if that model could have worked, if you could account for a larger, right now we are not building Baroque models of dark matter. We are assuming there's only one kind of dark matter. We might have to give that up. But we may have to give that up. But there is no evidence that shows that, okay, if you have two kinds of dark matter, maybe cold dark matter and something else, that it's like 40-50, 50-60, 60-40, whatever. At the moment, whatever it looks like, 99-ish% is consistent with cold collisionless dark matter, and maybe 1% other stuff. So we still, Occam's razor, we can still continue focused because we are trying to find the particle, right? So, yeah?
Collisionless dark matter.
Yeah, that is the model. That is the model, yeah. No, but the question, as I told you there, the problem is how do you arrest the growth and make it stop at 100 solar masses, between 30 and 100 solar masses. That is a window that was permitted where you could lock mass into those kinds of black holes without perturbing any other observations. Because if you had more massive black holes, you would see them traversing through gas disks, all kinds of phenomena. You would have seen them, right? Yeah, I'll show you what the constraints are. No, I mean, the idea that all of dark matter could be explained by primordial black holes whose growth has been arrested to between 30 and 100 solar masses could work has been ruled out. You cannot have all of dark matter in that way. One of the many problems we don't know how to arrest the growth is one of the big problems, right? The second is the IMF in the beginning during inflation. We don't know that either. So I have a couple of slides here. And from the fact that I have chosen some slides from Scientific American tells you that I just think it's highly speculative. It's a beautiful idea, but doesn't quite work. And so as you all know, the notion, okay, so I'm not going to go into details because this really detracts from what I want to do, right? They're not as relevant for supermassive black holes, but it would be remiss of me to leave them out completely. So the idea here is that you make primordial black holes very, very early on in the universe, and that you basically have, and the origin is a very large density contrast fluctuations that you have early on. So they're rare, but you will have them, and that those could actually form the more massive black holes. You form the seeds and then you grow them over time. So, and the speculation was that you would form it as a seed, and then the remaining would be orbiting massive galaxies. This is the model. So this is the diluted version where all the dark matter is not primordials, but some fraction is, in which case, where would these guys be spatially, right? If we were to go look for them, where would they be? They would be most likely in orbit, kind of stranded around the supermassive black hole. And there's a couple of simple things we can do. You can see why this idea was so alluring, right? So I just want to show you back of the envelope calculations that show you that basically there's some typical mass scales that, what could you have? So primordial black holes could have the horizon mass at the time of formation. We don't know when they form, which means many mass ranges are permitted depending on when we would like them to form, essentially. So if they form very, very early on, right at inflation, 10 to the minus 43 seconds or so, then they are likely, then the horizon mass at that time is about 10 to the minus 5 grams. So that is the typical kind of mass scale you could come up with at that time. If they form later, 10 to the minus 23 seconds, then they could have masses of about 10 to the 15 grams. But that is sort of the evaporation limit for the age of the universe, right? So if they formed much later, say at when t equals 1 second, then they could have a mass of 10 to the 5 solar masses, because by then that is the horizon mass in a standard lambda CDM cosmology, right? So this is just to show you the uncertainty in the masses that you could have for this primordial population, depending on when you want to make them, right? So that is one big issue, that this is unconstrained. And so there's a huge range of potential masses that you could have for them, right? And whatever you do, you need, as I said, the idea is that, you form them from the very large fluctuations. So you need very large inhomogeneities to collapse early on. So it's a departure, little bit of a departure from our standard picture that we have because of how rare those extremely high fluctuation regions would be. Once again, to account for all the dark matter that we see later, okay? So these are just to give you a flavor for what the sort of the real lack of constraints and the wishy-washiness of that model, right? And then what you find is if you look at the evaporation time scale, so all primordial black holes with masses less than 10 to the 15 grams would have evaporated by now. And they would have basically their evaporation would give you some, a background, gamma ray background population. So, yeah. Yeah. Well, it is permitted. The physics permits it. We just don't have evidence for it, right? So the physics permits it. And so it probably occurs in the universe, but we don't have evidence at the moment. But we have estimates. So, because we can estimate time scales and mass scales, it behooves us to try and see what would happen. I mean, I'm trying to find desperately some ways to constrain the model, right? So one constraint could come from evaporation of these black. As you know, evaporation timescales for any of our friendly supermassive black holes is completely irrelevant. Evaporation is completely irrelevant for any of the black holes, either the stellar mass or the solar mass black holes that we're looking at today, right? So, but so here you should find, if there was such a population, right? If you made them, right? If the universe made them in a whole bunch of different masses that I showed you, right? There's no constraint. You could make them any masses. Anything that formed with a mass less than 10 to the 15 would have evaporated by now, and it would have left a signature. You would have a gamma ray background, right? But, yeah. But that doesn't happen till much, much later in the universe, right? Because remember, these models, inflation, this is pre-radiation dominated era. So then you have a long radiation dominated era, then you get to the matter domination, and it's only then that they could grow faster. But whether they can grow faster than they can evaporate, etc., who knows? But the idea is that if they were there, they would leave a signature in the gamma ray background, and we don't see any signatures, right? Of course, we could make more precise, we need to make more precise measurements of the gamma ray background. But what you can do is you can look at the unresolved parts of the gamma ray background. We know the sources. We can remove known sources. You can look at the unresolved component, and you can speculate and say they all came from primordial black holes that evaporated. Even then, you find, that's the most optimistic scenario, that's when you find that it's less than 10 to the minus 8 of the critical density of matter. Okay, so it's really quite inconsequential in terms of the matter in, yeah. So that is the process that actually gives you, so that's what the evaporation will give you, right? So it'll form, you'll get photons. And for the mass ranges that we have considered, it'll give you 100 MeV gamma rays, which you can redshift away as you want. Yeah, this is taking into, yeah. So I just wanted to, since I knew that a lot of you would be very excited about primordial black holes, although they are not central to my lecture. So I have a bunch of references here of what I think are some interesting papers where people have looked at the constraints. And so these are the current constraints, right? And so I will just stop here with why it's even worth indulging. So it's worth indulging because obviously it would be nice to know if there are more than one pathway to make seed black holes, right, for the supermassives. And in which case, maybe they could form, these could be one way to form them. And then the other tantalizing thing, of course, is that there is no other way we can get close enough to the epoch of inflation. There's no other direct data we can get, right? We've gotten as close as we can with CMB, with polarization. It's unclear that we can get any closer. We can get better, but whether we can get closer, we don't think so. And so this might be one way to get much closer with more detailed data if indeed this happens. So I mean, I'm going to move on because I've spent way too much time on this. So this is the current status of, so you can take a look and see that in terms of the mass ranges that are permitted, what is open, and as of, and as I told you, this was all preoccupation was what fraction of dark matter could be constituted by these. And this is actually, it's a really, really tiny portion, as you can see. And so this is a very nice paper, and Bernard Carr also has a very nice review that came out, I think it was on AstroPH in 2018, but it came out in 2019, where he really talks about possible channels for early black holes, very massive objects in the universe, and so sort of the inventory, the sort of the lower mass part of the black hole inventory. So then I don't need to tell you this. Of course, this plot is already outdated as of even of my last run. It's hard to keep up now, and I find it quite incredible that now, there's an alert and yet another event, and that is it. We've opened the window, and we're seeing so many. It's so fantastic. It's thrilling to be alive when this happened. Hopefully, we'll be alive when Lisa does this for supermassive black holes. That sort of, so we've had sort of electromagnetic data from X-ray binaries for black hole masses, and now we have data from gravitational waves. And so yeah, so coming to this, so this is one of my favorite candidates for an intermediate mass black hole, and this is from an observed tidal disruption event. So you have an off-center source here, and we think that this is a wandering black hole in the outer reaches of this galaxy. And this galaxy has interacted, these are galaxy 1 and galaxy 2, they've interacted, there's a residual stream that's in there, and the TDE was observed around this source. And modeling the tidal disruption event of this source gives you a mass estimate for this source, which lies in the intermediate mass regime. And this paper came out in 2018. So this was a really, really beautiful paper. So now we're going to dive back into where we are in terms of our frameworks for understanding. So as you all know, so the basic idea here is that the accretion process essentially involves the release of gravitational energy from infalling matter onto the black hole, and that some portion, some fraction with some efficiency factor, if you will, of this energy, of the rest mass energy of the matter that is falling into the black hole is released as electromagnetic or other radiation, right? Other radiation here being gravitational waves. So some portion is actually released. And so this is the basic idea. And the idea here is that we know that matter actually falls in, makes its way from a distance, and that there are at various scales, there are going to be, so if I look at a galactic nucleus, then there are going to be various scales on which there is a mass inflow rate. And the goal is to couple the mass inflow rates at these various radii. How does the gas actually make it in? And so as I said, one thing that we are going to do is we are going to cut this piece out. We're going to try and understand how much of the gas flow we can model from here. Because a lot of the phenomenon where you release electromagnetic energy, and that energy is captured by us, by detectors, and it produces further effects of feedback, are actually seen from the outer regions, right? So that's why it's okay when we are studying that part of the phenomenology to black box the inner part and see what we can do. And so the way these sort of the macro model, if you will, works is that you have if you have any accretor of mass m and size scale or radius r, then the energy released per unit mass, delta E accretion, is just gm over r. And so, and this accretion yield, you can see immediately that the yield is going to, so this is the energy that's going to come out that can be tapped by the accretion process. It increases with the compactness of the source, right, for a given mass. And obviously, it's the greatest for the smallest accretor scales. So for example, if you look at the accretion onto a neutron star where you have roughly a solar mass-ish and a radius of 10 kilometers, then you see that the kind of energies that we're talking about are 10 to the 20 ergs per gram or so. And if you compare that with the efficiency of energy extraction with the nuclear fusion, you find that energy extraction from accretion is much more efficient than fusion, for example, where you get about 10 to the 18 ergs per gram. Okay? And so accretion onto a black hole will increase a much more significant fraction of the rest mass energy than does fusion for the binding energy. So it's an extremely valuable, energetically interesting process. And so you typically you need general relativity. After telling you that we don't really need general relativity all that much for the outer modeling, we sort of do, as I said, now and then, and you actually need GR to compute the actual binding energy per unit mass. And roughly the typical accretion yield when you do that calculation is 10%. And so this is the magical reason that eta parameter, or the energy efficiency that you see banded about in all accretion physics, is 10%. That's the origin of that. So, and this, of course, is one of the most efficient ways to getting energy from mass. So now accretion onto a black hole must power some of the most luminous phenomena that we see in the universe. So for example, we see quasars at great cosmic distances, and they are, as you all know, some of the brightest beacons in the universe. So if you look at the luminosity of accretion, then you find you can write it in this way, where eta is this efficiency factor, c squared times m dot, which is the mass supply rate or the mass inflow rate. So if you look at the luminosity of quasars, then you require that the mass supply rate for 10% efficiency needs to be about 1 solar mass per year. That's the kind of feeding rate you need. Because remember, I'm telling you that all I'm trying to figure out is the feeding, the mechanics of the feeding, of how much mass I have to move around. So if I look at, similarly, I look at X-ray binaries where the luminosities are several orders of magnitude lower, 10 to the 39 ergs or so, then the feeding rate is 10 to the minus 7 solar masses per year. And if I look at gamma ray bursts, which are even more, they're short-lived, but they are even more luminous than quasars, then you find that they can have extremely high mass accretion rates, 0.1 solar masses per second, right? So, and of course, you all know that, gamma rays for a very brief period of time, especially the short-lived bursts, so much energy is coming out in such a, they are sort of the most extreme events that you can think of. Okay, so then the way these models, the way we've been thinking about the physics of these models is that, accretion produces radiation, and we know radiation produces pressure, radiation has pressure, but will this then inhibit further inflow of gas, right? So the idea is that what are the basic, I'm trying to put together understand which are the most relevant physical quantities in this picture, right? And yeah. Yeah, everything is spherical accretion. Yeah, totally. It's a simple back of the envelope calculation to just get a feel for what's going on in the various sources. And as I said, the dream is to kind of integrate the sources across black hole mass in terms of physics, right? Okay, so the radiation pressure acts on both the electrons, but the electrons and ions, the protons, cannot separate because of the Coulombic force with the gas that is surrounding. So if you look at the radiation pressure on an electron, you find that this is the Thomson cross-section. Again, everything I'm talking about is in spherical symmetry. Then we can compare that to the gravitational force on the electron-proton pair. And you know where I'm going with this. I'm trying to come up with the understanding of the Eddington limit. So balancing the radiation pressure with the gravitational force in the innermost regions around black holes. So what you find is that you get an optimal accretion rate called the Eddington rate from this balance. And it turns out that the Eddington rate, what is great about that Eddington rate is that it depends mostly constants of nature and the mass of the black hole. So you can write it out as 10 to the 38 times m over m sun ergs per second. So this, if you will, in the classical sense, is the limit is the most optimal growth rate that you can have in spherical symmetry. I'm not talking about super Eddington yet. We're getting there, but this is the sort of the basis. So a lot of the modeling, as I said, super Eddington, once again, we haven't seen a single supermassive black hole that is accreting at super Eddington at the moment. So all black hole models that me and everybody else builds are actually Eddington capped, okay? And we may permit small periods of super Eddington accretion. We may say, well, our models are flexible to permit that. Small epochs, because we haven't detected anything, which means they are such small epochs that maybe we are not catching any of them, any source in that state, right? But basically, we assume that this is sort of the optimal rate. This is a limit that we have. And I'll just finish in a minute, yeah. And then what you find is that this can be then translated into a minimum mass that is required. So if you see a quasar, we know the luminosity of a quasar, then that is telling you that quasars, the brightest quasars, are powered by black holes, or about greater than 10 to the 8 solar masses. And the brightest X-ray binaries could be powered by sources that are more than, black holes that are more than 10 solar masses, yeah.
So, show that something is super Eddington or not, the velocity and mass independent.
Exactly, and we cannot, exactly. And that's the reason, and we don't have a way of making measurements for an accreting source that is independent of the luminosity output. Fair enough, yeah, fair enough, yeah. Yeah. It could be, yes. So,
If I try to increase mass in order to explain them, I don't know on the other hand it's really
exactly, yeah. That's right. So that's why I'm telling you that I'm not entirely bought on to the idea of super Eddington accretion, in particular for supermassive black holes. Because I'm discussing supermassive black holes in these lectures. I'm not really talking about. Sure. No, but the observational thing that I shown you does not suffer from that problem. That's why I keep telling you it's more convincing. Yeah, absolutely. Yeah, that's a fundamental limitation. Okay, so the question is that, now we find that in simulations, so GR-MHD simulations, so these are simulations where general relativity is fully modeled well, and you have magnetohydrodynamics, so you have seed fields, you have geometries of fields, and so on, which once again, cosmically, we have no idea how magnetic fields are born, how they grow, and how important they are on larger scales. Our idea of galaxy formation now, of how galaxies form, does not require magnetic fields, does not require magnetic pressure at all. Yeah. Pardon? Oh, yeah, the GRBs, yeah. Yeah, we think that, so gamma ray bursts we think are special sources, right? So we think that they are hypernovae. So that tells you something about what produces gamma ray bursts. That they are not single black holes around which accretion is happening like the other cases that we have considered. Yeah, because there's different physics. It's produced by different mechanisms, by hypernovae. Yeah. So it is coming from the gravity. So the energy that's tapped there is from the gravitational collapse of a star, of a hypermassive star. So there are it is not your classical having a little black hole around which you're finding accretion. So the source itself has a different nature. But I mean, I did that only because, I wanted to show you that there are more energetic phenomena in the universe, not claiming that they're all the same by any means. Okay. So these GR-MHD simulations, what they find is with those initial conditions, they can find accretion at rates that are well above the Eddington rate. So it is not a rate that is capped in those simulations. So these simulations are on very small scales. They require initial conditions and priors on magnetic fields, geometry of magnetic fields, strength of magnetic fields. I mean, one can argue they are not very strong magnetic fields that you need, they get amplified, etc., etc. But the origin of these magnetic fields on large scales in cosmology is really unknown at the moment. But the point is you can get super Eddington flows in these simulations. We are yet to find them in any objects that we see to infer those rates. Okay, So the Eddington limit, so what is interesting about this Eddington limit and the fact that it scales only with the mass of the source is that you can actually get a mass growth rate if you assume that that is an optimal rate and things are capped at Eddington. So then I just rewrote that equation, nothing dramatic here. And what you find is that because of this, because the luminosity of accretion is m dot eta c squared, and if you are accreting at the Eddington rate, so then you are capped by, at this rate, then you find that the mass growth is exponential mass growth, okay? So this is the initial mass, and over time, the mass buildup will be exponential. And so then the question is, okay, that's great, but what is the time scale? So it turns out that this sort of typical time scale, which is derived from these fundamental constants, you get this time scale, which is the saltpeter time scales. That's few times 10 to the 7 years. So this is sort of the relevant. We start out building models for black holes and the population of black holes starting from some initial seeds and so on and so forth with these kinds of numbers in hand, okay? We say that its luminosity is capped at Eddington. Then the relevant time scale for mass doubling is about, and so why is this relevant? This is relevant because then any process, any physical process that delivers gas to the center, right, the time scale has to be shorter or comparable to the saltpeter time scale to grow the black hole efficiently. If it's going to take the age of the universe, like 2 orders of magnitude more time for the gas to actually make it in, this is not how the black hole is going to grow, right? So remember, black holes can grow by and large 3 different ways. Again, this is supermassive black holes. Everything I say is pretty much limited to supermassive black holes unless I explicitly tell you it's valid for stellar mass as well. So supermassive black holes, we believe, can grow either by direct accretion of gas, so that's all of this phenomenology, direct mergers, so merger with another black hole, or obviously the compounded situation where you have merger and you are making the gas inflow, accretion inflow, you're triggering an accretion episode, which can be more efficient than your average Eddington rate when you merge. So those are the only 3 possibilities. The question then for modelers like me is, if I give you the black hole at the center of M87 today, what is the likelihood? What portion of it assembled by pure accretion? What portion accumulated with mergers and merger-triggered accretion? So that's what we want to do. We want to understand, by and large, we now know that most of the mass assembly for supermassive black holes is driven by accretion. And it's only for the most massive black holes at any epoch, say today, so in M87, for example, that for the most massive black holes at every epoch, there are mergers become relevant at very late times. Because, you can see why that is, because the environments are going to be cluster environments, and you have galaxies falling into clusters and merging, getting stripped, and the black holes falling in. So that mode becomes important for the black hole that is in the center of the brightest cluster galaxy. And that guy is already a super duper massive black hole to start with. So at late times, for the very massive black holes in the centers, in the densest environments, mergers become an important way to grow mass, right? So once again, we want to see what is the balance of growth contributed by these 3 modes for any initial mass starting from some initial mass to a final mass over cosmic time, right? So that's what the models are very rich in the phenomenology, as I'll show you later. Gosh, I'm going very slowly. I have 16, what? This is today's. That's it? Shoot, I have like 83 slides that I made for today. Okay, I might have overdone it too. But okay, so then, okay, the other piece of the phenomenology is how do we connect the data, right? How do the observations feed into any model that I'm going to build? So I've already shown you the key ingredients in these models are Eddington luminosity, time scale, and the relationship to black hole mass and accretion rate. So that set of parameters. The next thing is, of course, how do I connect it to the data? So then you want to see what is the emitted spectrum of such an object, right? So what is the re-radiated energy in the electromagnetic spectrum that comes out? So then you can do a simple back of the envelope. Again, this is back of the envelope, the most sophisticated models. There's very good radiative transfer that is now done. But this is just to give you a feel. give you a sense, right? So there are two extreme possibilities, as you all know. One is you can just say all the energy is thermalized, right? And the radiation basically emerges as our favorite black body, right? And the characteristic temperature then we can actually calculate will just be the accretion luminance. This is Stefan Boltzmann's law, so you can all see that. And that if this luminosity comes out, if all of it comes out thermalized, obviously when I'm going to do the two extremes, you know that the real universe is the sum of the two, somewhere in between. We can bracket the extremes. And then here you assume that, so for example, you can then say if that is true, then we can estimate the black body temperatures of these objects that compact objects. And so for example, for neutron stars, you can see that the black body temperature is about 10 to the 7. The reason this is important, this will tell you which wavelength all the radiation is likely to come out. So, and so the other possibility, when it's not thermalized, right, is that you can think about the gravitational energy of every accreted electron-proton pair. It gets directly converted into heat via shock with some temperature Ts, right? So this is a non-thermal case. And what you find is then in that event, 3 kTs is going to be this gravitational energy released. And then that would give you, suggest a temperature that is 10 to the 11 K. So the typical photon energies that come out that signal accretion onto a compact object is happening will come out between those two limits that we just saw, right? 10 to the 7 to 10 to the 11 for the case of a neutron star. So then you can see that's about 50 MeV, so you expect accreting neutron stars to be mostly X-ray or gamma ray sources, similarly stellar mass black holes, right? And so this is by and large fits our image of where we are seeing the accretion coming from these classes of objects, right? So for supermassive black holes, you can plug in the relevant mass, right, which is 10 to the 8 solar masses or so. And then what you find is the black body temperature is about 10 to the 5. And the temperature, the shock temperature that you get is the same, roughly the same. So once again, you expect supermassive black holes, though because this temperature is much lower, you expect them to glow in the UV as well. So you have a UV bump in the typical, we'll come to that later, the details of the spectrum. So this is just to give you a feel for what are the key basic properties of these objects, connect a simple physical paradigm to observed numbers to see if they make sense, okay? And so they all make sense. This is a good sense of a fit. Okay, so then to model this an accreting source, we need to figure out the nature of the objects. You have to pick whether you want a black hole or a neutron star, and you have to model the observed components in the radiation, as we just saw, the various wavelengths that will be implicated. And then we want to, because we are sticking to this sort of baseline Eddington paradigm, we want to choose a minimum mass for the object that is in concordance with the Eddington limit. So then what is the challenge? So now we have the basics. The challenge now is that we need the physics to arrange an accretion rate to provide the observed luminosity. And so we need to provide this mass inflow rate. Whatever scale of the problem you now want to focus on, that is what we need to do. We have to solve the feeding problem. That's the feeding problem. And then we might have to figure out the time scale. So if I want to explain the growth history of black holes and assembly history over entire cosmic time, then there's the timing issue, so the growth problem, right? So these are sort of what one can do. And I think I am going to focus in my lectures mostly on sort of the AGN case, supermassive black hole case. And, these problems are better understood for binaries, much cleaner in terms of much more detail. They're cleaner systems. These are much more complicated systems because they are embedded and sitting in the centers of galaxies. And so, a lot of in terms of the history of the subject, a lot of early work was done really here. And, the work on AGN has really been pushed in the last 20, 25 years. So I'll give you I'll just quickly go through this because, I don't want to spend too much time, but I just want to show you how these connections, is to show you an approach to modeling as well. So that's really my goal in these lectures, right? How are we approaching? It's a complex problem. How do you approach the modeling? And the modeling approach, and this is a larger sort of issue of looking at very complex problems in astrophysics, not just this one. The idea is, and this is, obviously this is a personal take, and this is sort of how I work. So you first build a pared down model. So to build the pared down model, you need to understand what are the essential pieces of physics and what is superfluous to start with. And then you build more and more complexity into the model. So you have the pared down model, you milk the model as much as you can. It will have limitations. And then you pick what additional bell and whistle you're going to add that is supported by the data. And so you add one piece at a time to make it more and more complex so that by the end you come to as much complexity as is experimentally supported at that moment, right? So those are the kinds of models that I build, and I think that that is sort of the approach that most people have. It's a most fruitful approach in astrophysics because our systems are so complex. Okay, so this is again okay. So let me move. So this is, I told you, this is the broad brush for this accretion model. So how do we delve a little deeper into the physics and try to understand the flow onto a galactic nucleus? And so what we find, so now we are at 10 to the 5 Schwarzschild radius or so, 10 to the 5, 10 to the 6 Schwarzschild radius. We've kind of zoomed, we talked about there overall. We're sitting far outside, we black boxed everything, Eddington rate. Now we're like, okay, let's get closer in and let's see how do we model the physics. How do we model the flows of the gas? It's not enough just to say m dot. How does the m dot actually occur at that physical scale? So this cartoon, we want to know what governs m dot here, what governs m dot here, because we want to see how m dot actually changes as we go closer. So one interesting way that has been used to model that stage, about 10 to the 5 Schwarzschild radii or so, is this paradigm of Bondi-Hoyle Lyttleton accretion. What it is just a very simple model where you are looking at the accretion of zero angular momentum material. People have gone beyond that now, but this is the basic idea that was there, by an object that is now moving supersonically through a medium of constant density, so there is no self-gravity. And so either the compact object is moving or the gas is moving. It doesn't matter. You can pick one or the other, right? So this is the case where you are sort of on these scales and you're looking at gas that is rapidly moving to the center. So then the idea is that the gas can get accreted by this compact object, and you can calculate a mass accretion rate, the Hoyle-Lyttleton rate, which here is proportional to the mass of the object square times the, so this is an infinite, it's a medium, an infinite medium with some ambient density, rho infinity, and that, as I said, is used to model sort of something here. And then what you find is that you can, once again, we are trying to see how do things scale? What are the relevant physical quantities that we need to worry about and how things scale? So what you find is that for this stage, we can use the Bondi-Hoyle prescription. If I have time, I will go a little bit more into detail, but you can look up this derivation. It's very standard. There's nothing deep here. The only thing to show here is that in this scenario, what you find is the accretion rate is proportional to m squared. Okay, so that's all we need to understand now, okay, in terms of a refinement compared to what we were looking at with the black boxed Eddington rate. Okay. Because when we were looking at the Eddington rate, we were really looking at the balance between the radiation pressure and gravity, right? And here we are just looking at the dynamics of the gas that actually makes it with zero angular momentum onto a compact object. So, and as you all know, that the transferred mass that is flowing in is not going to hit the accretor in general because the accretor is so compact that it's almost like having a target that, if you're hitting a target with an arrow and the target is so small that you're never quite going to hit the bullseye. You'll always hit somewhere that is a little bit further out. Because there's angular momentum and the compact object is gravitationally strong, it will couple that flow, turn it around, and you will assemble an accretion disk. So you can see, once again, why you should have an accretion disk geometry. Right? So the initial orbit will actually be a rosette for the gas, but then there are all these self-intersections. They will fill in the orbits, and you get what we geometrically think of as an accretion disk as the way to finally deliver the flow here. So what this is teaching us is that the geometry of the flow, by the time you get down closer and closer in, is that you will be making a feeding disk. The structure you end up forming here is an accretion disk. So you end up having a feeding disk, and from the inner edge of the feeding disk is where the gas finally makes it onto the black hole. Once again, I have not told you anything about the mass loss. Does everything that flows past here make it in? It turns out that is most critical here, that you could have a huge amount of mass loss that is either manifested as outflows, which are seen. So you see large-scale outflows on these scales driven from here. So we know that not all the mass is from that Bondi rate. That entire Bondi rate supply is not the true supply rate for the growth of the black hole. So we know that now. And we know that, so we're like, okay, how do we figure that out? We figured out that the physics then tells you you need to have a feeding disk. So then it's the inflow rate from the inner edge of the disk where it's at in terms of black hole growth. Okay? And so what you find is that for these disks, basically the gas follows Keplerian orbits, which is the lowest energy orbit for fixed angular momentum. This gas does have angular momentum, and that's a circle, so you have that. And once again, right, so we have this feeding disk, but what we don't know, once again, is how the mass actually flows through the disk itself. And so then we have this other hand-wavy model for viscosity that is going to actually drive the mass in and the angular momentum out. So this is just to show you how you keep adding complexity as you get closer and closer into these models in terms of scale. Excuse me. So the transferred mass, as we just saw, but it kind of orbits it. And so so this disk structure has to do two things for us, right? It has to allow some fraction of the inflow rate outside the disk to actually make it into the hole. And the way it has to accomplish that is to somehow exert viscous torques. That's the model that we find compelling now, that will actually move the angular momentum out. So this disk is going to be the device that is going to get rid of the angular momentum of the gas, because you need to get rid of the angular momentum of the gas for it to finally plop onto the black hole. That, again, as I said, is not solved. So there's another heuristic idea that we have there, which is of an accretion disk in which you have viscous transport driven by viscosity. So viscosity just between the neighboring shearing annuli of gas, the motion in neighboring layers, that dissipates angular momentum. There's a net unbalanced torque, and that moves the mass in. So we've kind of figured out how you could get it to work. It turns out it's not the full picture still, right? And we still find that the gas can actually and will hang in at a much smaller radius. This is not the most efficient way of getting rid of all the angular momentum, although this is one way, okay? So basically, accretion requires, so this disk structure and the final accretion is going to require that all the angular momentum in the gas be lost. And so then you can actually calculate what is the angular momentum, what is the radius of the final orbit, how much that orbit has to shrink, right? So because remember, that's the energy that we're getting rid of, the angular momentum in the orbit. And then you find that the energy loss through dissipation is actually quicker than angular momentum loss. So we think that basically matter will spiral in by a sequence of circular, whatever Keplerian orbits. The orbits will shrink and get smaller and smaller, and eventually they will fall in. Okay, so this is the accretion disk. So this is, in case you wondered why this accretion disk is where you ended up with. So today I was just trying to show you that these are the elements that you build up, and you see that inevitably that's what it works. That works. So then if you have an accretion disk, there are particular properties. Oops, okay, I'll just go over for 1 minute and then we can break. Because I think it'll be nice to stop here, because then I will really stop where we are at in terms of the details required for modeling. So the accretion disk structure, we believe that it's a flat, differentially rotating gas disk. It has some vertical scale height, h of r. And it has a surface density per unit area, sigma of r, which is this rho times the density times h. Has a rotational angular velocity that increases towards the center. It has an angular momentum that decreases towards the center. And then you can see that this structure, then putting it in terms of this structure, allows you to then play with the geometry of the disk. So you can play with the geometry of the disk by taking various values of h over r. So this is scale length as a function of the radial extent. So for a thin disk, h over r is much, much less than 1. And it's all Keplerian, so you can actually see the velocity of the gas on the orbits as a function of radius. And so now the question is, let's say you are in a thin disk, so we've established all of this, the structure, the gas actually makes it in. The question is, does it cool before it makes it in? How much of it makes it in, et cetera, et cetera. So essentially, disk formation is unavoidable, and that you always form an accretion disk. And now the fundamental question is that the disk must be small enough. The feeding disk has to be small enough for matter to accrete on a reasonable time scale. And on scales of 0.1 parsec. So for a supermassive black hole, that's where you can bring things down to with this game, okay? But feeding supermassive black holes is actually quite difficult, it turns out. So getting this whole structure to work and to have the kind of feeding rate that you need to grow these supermassive black holes is actually quite hard. And maybe that's one of the reasons why you see phenomenology from data shows you that the mass of central supermassive black holes is only 1,000th of the mass of the bulge, which is the stars in the bulge, right? That maybe growth is kind of inefficient for black holes compared to the assembly of stars around them, right? So that's what we are combining. Okay, and these accretion disks are universal, and let me see how much more I want to, where more I would like to go to today. Yeah, maybe I'll just do 2 more slides where I'll just talk about, what are the pieces, the other bits of physics that go into accretion disks, right? Which is the driver of the accretion process, as I mentioned, is viscosity. That is the relative shearing motion between neighboring annuli of the gas. And it's a dissipative process which will transport angular momentum outward and mass inward against the angular momentum gradient. It's currently unknown. What microphysics does it is unknown. We believe that magnetic fields might play an important role there. And you can therefore calculate, if you want viscosity, and you say it's molecular viscosity, then you can actually do a couple of back of the envelope calculations to see what are the relevant scales, and then see how they fit into our supermassive black hole problem, okay? And maybe I should stop here, right? What do you think? Okay. So I think what I want to do, so when I start tomorrow, I'll start a little bit more about developing this picture, because this is going to be the crucial picture in terms of the mass inflow rates. So we are going to be able to get the modeling down to the stage where you have this accretion disk, and then you have an m dot from the inner edge of that accretion disk. And that is the mass buildup rate for the models that we're going to look at for black holes. And then we look at the cases. Obviously, this is one particular geometry. H over R is much, much less than 1. I'll talk very briefly about other cases where you don't have these thin disks, but you have thicker disks. Phenomenology is slightly different. The processes, timescales, slightly different. And therefore, the observational signatures are also slightly different. And current observational data suggests that we have to look at that case. We have to look at the case of different geometries and different ranges of accretion rates, both of those, right? and also cases where, to connect with the observations, cases where you basically have a mass accretion rate that is very high. So the mass growth rate is very high, but it's a flow which is radiatively very inefficient. So the luminosity that you get out of that corresponding mass accretion is much, much lower, sub Eddington. So it's not like Eddington. So by measuring just the luminosity, you will not infer the right mass accretion rate because it's a completely different geometry. So those are the various cases. As I said, right, we build a bare bones model and then we keep adding the complexities. So anyway, I'll just stop here and I'll continue next time. Thank you very much for your attention. Yeah, oh, it was there. Sorry, I didn't notice. I was telling myself I need to get more water. Yeah.
So I think I understand this Bondi-Hoyle accretion. How does the gas get this angular momentum, and what determines the direction of that?
Oh, no, in the Bondi-Hoyle picture that I was showing you, there is no angular momentum. It's zero angular momentum flow. So there have been modifications where people have proposed, like Andy Fabian and Ramesh Narayan wrote a paper where they tried to look at finite angular momentum gas flows, and there's a modification to the Bondi-Hoyle. It is less efficient than the case where you assume zero angular momentum, obviously. Yeah. Right now, that's what we do in the modeling. But you know, GR-MHD simulations, which access the inner region, the inner edge of the accretion disk closer in, even there, they think that jets might originate from there, but you know, jets are really not a solved problem. So they have initial conditions. All I can say is they have initial conditions that start off with the inner part of the accretion disk from which they can drive outflows in jets at the moment. But how that scale is connected to the large scale radio jets that we see, no idea quite yet. We don't know. I mean, there are, again, models that try, but to connect the smaller scale physics to. I think part of the problem that's happened in the theoretical work, in the simulation work, right? It's very sophisticated, and it requires a lot of priors in their initial conditions to get it to work. They work beautifully. They can resolve scales that are spectacular. But how all of that connects to the rest, you know, this kind of cascading picture that I'm trying to show you, that's been very challenging. So we've really not connected yet. And I mean, the only problem where I think there have been some, what I think are good attempts are in trying to model the energetics of outflows and feedback. So there's two models that I really like, and in the last lecture, I will show you those two models. One is by Gaspari and collaborators, which is a more recent one that is very, very nice. And the other one comes from Ramesh Narayan's group, where they have come up with a model. It's still phenomenological. They can't physically tell you how the various scales couple, but they can start from the GR-MHD model that assumes a lot of initial conditions, magnetic field strength, et cetera, geometry, et cetera, et cetera. But then from there, they are able to take the outflow values for m dot, propagate them in the larger accretion disk to map energy exchange. And so they've been able to successfully couple the energy output from these outflows, not quite the mechanics of the outflow. Then they can't do simultaneously, they can't tell you if gas is pushed around physically and moved, or it's just energy that is moved. So they can do the energy part very well now, and those are very nice. Yeah. Yeah. Yeah, so Daniel Proga and collaborators, I mean, there are other people who have worked, so that's a slightly wider view than the GR-MHD view. So these are relativistic hydrodynamics without GR. So, you know, because by the time you get to the outer part of the accretion, the mid-outer part of the accretion disk, GR is not as important. So you can do that without the GR. And so there have been groups that are modeling outflows very nicely as well. As I said, the problem is that, numerically, because of limits of various techniques, hydrodynamics, whatever techniques that you use, and adaptive mesh refinement, each of those techniques has its limitations, which means it is well attuned to study certain scale, certain slice of the problem. And then connecting them has remained a challenge and does remain a challenge. However, as you'll see, even without connecting all the dots that are even currently available, we can explain a lot of what is seen observationally. I think it's quite spectacular. In both individual sources for individual modeling of detailed modeling, I mean, Prajwal knows that, right? I mean, there are some individual sources that you can model spectacularly well with the spectra, with inflow rates, I mean, with just these models, right? And you can model them extremely well. But what I think has been super exciting in the last decade is that you can model the population properties as well. And because, a lot of what we see are, the observational data is often globally average data. So for example, we see that the average accretion history of black holes over cosmic time and the growth history, assembly history of stars. So this is for all galaxies, right? So this is a globally, so it looks something like that. And so this is star formation rate, and this is black hole accretion rate. I mean, there's a huge factor of, 10 to the 3 or something. They're not on the same plot. This is much suppressed, but I multiplied it by 10 to the 3 to put them. And what you find is that they both peak. So this is as a function of redshift. So this is 0 and this is 6 or something. So what you find that z equals 1 to about 3 is when they both, so this tells you that by and large, star formation activity in galaxies in the universe traces, or it depends on what you see as primary cause and effect, right? That black hole accretion rate and star formation rate track each other cosmically. This does not mean they track each other in every galaxy. So what happens in an individual source is different from the population-wide picture, this is why I keep repeating myself saying, oh, we can do really well for an individual source, but that we can do spectacularly well simultaneously for individual sources. Not all sources, because we don't have the data for all of them, for the ones that we do, and for the population. So that's what the power of the modeling is at the moment. And that of these very simple kind of pictures that you can build up. And that you can go quite far, with explaining what is seen now. Because the gas supply, right? So the gas supply in the universe has been absorbed, right? So we are in a gas-poor universe at late times. Most of the mass is locked up in stars already. Most of the gas mass is locked up in stars, and black holes have accreted. This is why we believe that all the nearby supermassive black holes, when we do the demographics of the population, they are all dormant. They're not growing, right? So the M sigma relation, that correlation that you're seeing, those are dormant black holes. And the way you are finding them is by mapping the orbits of stars right around them, which tells you there's a central massive object. Whereas the X-ray data, you're seeing active black holes, actively growing black holes. And so by this time, if you plot an omega gas for the universe, the gas content of the universe, that's what this is mirroring. It looks something like that. So the gas content of the universe is falling dramatically because most of the gas mass that you had early on in the gas-rich universe has been locked up into stars and into black holes, right? So we are assuming that it's real matter that is feeding down black holes, right? So that's what this is reflecting. And this is in agreement with the fact that all the local black holes, supermassives, are not feeding. Most of them are dormant. Yeah. Pardon?
The total mass and stars should somehow trace the total mass of black holes.
Not necessarily in an individual, that's what I said. Not necessarily in an individual galaxy, but they sort of do, right? That's what the correlation is telling you. M sigma is telling you that. Yeah, that in the inner regions, not the entire extended stellar population, but in the inner regions. And it's telling you that it's about 1,000. Yeah. Yep. Pardon? Yes, you can use the same formalism, except the phenomenology is slightly different, because in stellar mass black holes, binarity plays a much more important role than it does for supermassive black holes. So there are much more specific geometry. So you have one compact object, it has an accretion disk, and then you have another object that may or may not be a compact object. It can be a star, it can be a main sequence star from which you're pulling mass out, etc. So the actual geometry, the formalism of how the gas makes it, etc., yes, that follows. It can be scaled. But the actual larger scale environment is fundamentally different. Oh yeah, absolutely, absolutely. You mean these are, obviously in the case of, in all these cases, right, in supermassive black holes, we are looking at galaxies that are fully formed. So these galaxies have already separated out from the Hubble flow, right? So these are actually collapsed perturbations. These are like closed boxes already in the universe. It's just that within this box, there are flows. So there are cosmic filaments that are feeding flows that are coming into the box. Yeah, yeah. The large-scale expansion of the universe, the local dynamics, the fact that Andromeda is falling towards us, or it's a freak case, right? Almost everything else is hurtling away, and Andromeda is falling towards us. Those things are completely irrelevant for this problem. Completely ignored. They're completely irrelevant. Because we are looking at cases where the perturbations have all turned in, they have formed these black boxes that are galaxies, even in the pre-galactic universe. When I talk about formation of the first black hole seeds, even by then, the large-scale expansion of the universe is not relevant at all.
Okay, so I think we'll stop with the moment. So thank you, Priya, for this.
Yeah, thank you very much. Thanks, everyone.
Meeting this wonderful lecture.
Thanks.
So